In the last video, you learned about adding vectors that are parallel or perpendicular to each other, and about the graphical method, which involves having to put the two vectors that you're adding together tip to tail. In this video, we're going to learn about what happens when we have to add two vectors that are not parallel or perpendicular to each other, kind of like the green and the pink vector that you see here. We'll start out with the graphical method, which was discussed in the last video. That means that we have to put our two vectors tip to tail on an axis, and you'll notice that I've done so with these two vectors right here. So then my resultant vector would end up looking something like this. The tail of my resultant vector is at the tail, or kind of the beginning of my two vectors when I've added them together, and the tip goes with the tip. And I could determine this vector, I could determine its components looking at my graph. So the x component of this vector is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, a positive 14 because it's to the right, and the y component is 2, a positive 2 because it's up. We could then find the magnitude and the direction of this vector based on its two components, similar to how we did in the last video. But what if I don't have a perfect axis like this, which we're not always going to have? Often, instead of having this nice axis, we really just have two vectors that we're drawing on a piece of paper. So I've come up with 6 steps to help you add any number of vectors. We can do this for more than just two vectors. So here you see these 6 steps. Pause the video for a moment and copy them down, and then we'll practice using them with an example problem. In this example, we have an airplane that flies 2 different displacements, and we want to know the total displacement of the airplane. As with any vector problem, we'll start off by drawing a diagram. So my first displacement is 75 kilometers, 30 degrees west of north. So starting off, it's often useful to draw that xy axis to begin with. And then I want to go 30 degrees west of north. That would be like saying 30 degrees to the left of the positive y-axis. So that vector looks something like this, with the 30 degrees being marked in here. And it's 75 kilometers. And then it says the second displacement is 60 degrees east of north. That's the same thing as 60 degrees ISP. Sorry, take that back. 60 degrees east of north would not be the same thing as 60 degrees ISP, but it would be 60 degrees to the right of the positive y-axis. Often it's helpful to draw an xy axis again before I draw this vector tip to tail with the last. It's 155 kilometers, so you'll notice that I've been careful to draw this longer than the 75 kilometer one. And the 60 degree angle would be located right here. So my resultant vector starts out at the very beginning of that 75 kilometer vector and goes to the end of my 155 kilometer vector. This is my total displacement vector. Now we have to solve for this. So I've taken care of step 1, drawing the diagram. The next thing, step 2, is to split each vector into its x and y components. To do that, I'm going to draw each vector by itself and then make sure that I draw each component as well. So here's my first vector. It looks something like that. And if I'm drawing its components, I always start at the tail of the vector when drawing the components. And I like to draw the components so that the angle that we are given is inside the triangle. So I'll start with the y component, and then there's my x component. As you're drawing the components, you really shouldn't need to even pick up your pencil. My 30-degree angle that I was given in the problem is located right here. and this has a magnitude of 75 kilometers. Pause the video right now to find the x and y components of this vector. That way you'll be able to check and see if you really understand finding components. I decided to call this vector A. So in calculating the components of vector A, I found that the x component was negative 37.5 kilometers, negative because I noticed that my vector is pointed to the left, and my y component is 65 kilometers. That's rounded a bit. I'm able to tell what those components are by using the sine and cosine functions. Now we need to do the same thing for our second vector. We'll call that vector B. So again, I'm going to draw a diagram, and then I'll draw its two components. First I'll mark that this is 155 kilometers. And this time we were given this angle here as being 60 degrees. So the y component would look like that, and there's my x component. Once again, pause the video and find what those two components are equal to. Hopefully you found the x component to be 134 kilometers and the y component to be 77.5 kilometers. Both of these are positive because the y is upward and the x is to the right. You'll also notice, if you take a look at how the values were given to you, for our first vector, it says 75 kilometers at 30 degrees west of north. Since west would be considered the negative direction, it has a negative x component. Both of these have north, so their y component is positive, and the second displacement has east in its direction, so its x component is positive. Those are just some hints to help you get those signs correct. The next step of the process in adding vectors is to add together all the x components and add together all the y components. In this problem, we only have 2 of each, but again, that method could be used for adding 3 or more vectors as well. So I'll call my resultant vector r in this case. And so Rx is obtained by adding Ax to Bx. And that means that it has a value of 96.5 kilometers. You'll notice I'm not really following proper sig fig rules here. That's totally fine, as long as your final answer has proper sig figs. For the y component, I'm adding that 65 to the 77.5. And as a result, I get 142.5 kilometers. Now that I have a vector, I have its x and y components, I can draw the vector. It's almost like I ignore the rest of the problem as I'm doing this. So the x component is positive, which means it's to the right, and the y component is upward because it's positive. So my resultant vector looks something like that. Now, if you were careful when you drew your original picture, you can take a look at it and make sure that the two look somewhat similar. You'll see that mine do look somewhat similar, and that's a good hint that I'm on the right track, that I haven't made any goofy errors along the way. So now that I have an x and y component, and I have a nice right triangle here, I can find the magnitude of my resultant by using the Pythagorean theorem. The square root of 96.5 squared plus 142.5 squared. That yields a magnitude of 172 kilometers. But remember, we also need an angle because we have to tell a direction. I always prefer to choose the angle that is within the triangle, but if you have a different triangle, you might be choosing a different angle, and that's totally fine. The biggest thing to remember is that you must choose the angle that is located at the tail end of your resultant vector. I also prefer to use the tangent function to find this angle. this angle is equal to the inverse tangent of 142.5 kilometers divided by 96.5 kilometers. That gives me an angle of 56 degrees. And if I draw an XY axis right here, I could see that that angle is either ISP, in standard position, or north of east, or above the positive x-axis. If you had found a different angle, in other words, if you drew your diagram differently and so ended up solving for this angle, you would have found the angle to be 34 degrees, and east of north would be your direction there. One more example problem for us today. In this problem, we have a dog searching for a bone who walks 3 different displacements. We're trying to find the dog's resultant displacement vector, which means we're adding together these 3 displacements. Even though there's 3 this time instead of 2, we follow the exact same method. So the first thing I want you to do is to start out by drawing a diagram showing all 3 vectors tip to tail, like they would be properly when you have to add them. Pause the video and do that right now. Hopefully your diagram looks something like mine. The 3.5 meter vector should be a pretty small one pointed downward. The 8.2 meter vector is pointed at that 30 degrees north of east, and that angle measurement would be right here. And then the 15 meter vector is pointed directly to the left or west. So your resultant would look something like that. Now your goal is to go through the remainder of the steps to adding vectors together. In other words, you're going to start by finding the components of each of these 3 vectors. Then you'll add together all the x components, add together all the y components, draw your resultant x and y component, and then find your resultant vector. Make sure to show all of your work and bring it to class with you the next time we meet.